Hi there guys, my name's John. Welcome to this video. I'm a mathematics tutor and I specialise in tuition and support for A-level maths, A-level further maths, including 6th term examination papers and mathematics admissions tests. Welcome to this video where we're going to take a look at a problem that I've selected from a past paper for the 6th term examination paper. So we're looking at step 2 from 2019 and it's question number 9 that we're going to be taking a look at. So this is from the mechanics section. It's not very often that I go onto the mechanics section. I usually stick with the pure maths and the statistics side of things, but I ventured into mechanics here just to do something different. So I hope you enjoy this. This is a really good problem, by the way. I've selected this problem because there is a part of this problem that is, it's not a particularly difficult part of the problem, but I think it could be something that if you're not careful could really trip you up. And I really want to draw some attention to that. I'll explain more when we get to that point in the video. I will leave a link in the description to this video so you can download the past paper for yourself. And I'll also, at various points throughout the video, put the question up on the screen so that you can see it as we're actually working through it. Okay, so the question is this, or the information that we're given initially. Before we get to the question, let's have a look at the information that we're given. So particle P is projected from a point O on horizontal ground with speed u and angle of projection alpha, where 0 is less than alpha is less than pi by 2. So we're in radians here. Really make sure that you understand the information that you've been given and that you pay attention to it, because some of these bits of information are going to be very relevant in quite subtle ways as we go through the problem. Okay, so my advice here, as things stand, this resembles just a normal A-level mechanics problem. Okay, projectiles, free fall, whatever you want to call it. There's nothing particularly difficult about this information, but when you're doing step problems, because the problems are much less routine, sometimes you've really got to understand why you're being given a certain bit of information. Okay, which, so to a certain extent, when you're doing normal A-level maths problems, sometimes the information is just so it's almost you're consistently given the same information. You can almost switch off to it, become desensitized to it, because you just kind of expect it. And you don't necessarily have to think too much about how you're using that information. You don't really have to understand sometimes. Whereas on a step problem, these bits of information really start to have an impact into the things that you're allowed to deduce, that you're able to deduce at certain points in your calculations. So for example, the fact that we're told that the angle of projection is alpha, where 0 is less than alpha is less than pi by 2. There are certain points in the calculations that we're going to be looking at in this video where it does actually creep in. And if you didn't have that bit of information, you wouldn't necessarily be able to make certain assumptions. Okay. Right, so by the way, I've got a bit of a dry throat today, so if I do seem to be coughing quite a lot during the video, then excuse me. What I would recommend is that you draw a diagram to represent this information. Now, I find diagrams very useful for the simple reason that you can summarize visually a lot of written information in a single diagram. So I've got the typical diagram that I would draw here behind me. So particle P, angle of projection, initial speed of projection, and so on and so forth. So the horizontal axis is the t-axis here, and this would be, well, whatever. Okay. I can see all of the information that I've been given in this diagram at a glance. I do recommend that you draw diagrams, not just for mechanics, but for your pure maths as well, and maybe to a lesser extent, but possibly also in your statistics. If you're not in the habit of drawing diagrams, then you might be making life difficult for yourself. Even if you consider yourself not a very visual person, you might be surprised that once you start drawing diagrams, you'll see how beneficial they can actually be. And it does take some practice sometimes, but notice that in your textbooks, in your maths textbooks for A-level, there will be a lot of diagrams. Okay, and this is no accident. Okay, so let's have a look at the first question once I've had a sip of coffee. Okay, so part 1. Show that if sine alpha is less than 2 root 2 over 3, so if sine alpha is less than 2 root 2 over 3, then the distance OP is increasing throughout the flight. Okay, so first things I guess that we're going to need to do here is, well, what we ultimately need to do here is to find a function, an equation, or an expression, should I say, to express the distance OP algebraically. Okay, so that means, how am I going to get that? Well, really I need to find maybe the displacement vector OP. So the displacement of P from O at time t. Okay, this is a fairly routine thing for me to calculate. So let's start out with that, because displacement and distance, they're very closely related concepts. They're not the same thing, however. Please remember that. I'm sure you do know this, but just a reminder. Distance, displacement, not the same thing. Distance is a scalar quantity. Displacement is a vector quantity. In the same way that speed and velocity are not the same thing. There's various relationships between speed and velocity, between distance and displacement, but they are not the same thing. Okay? So this is going to be a typical SUVAT equation, a SUVAT problem initially, because we've got constant acceleration. We don't have to worry about air resistance and things like this. By the way, when you do draw diagrams, don't worry if your diagram is not perfect. It just needs to be something that's workable for you. I know that P is going to follow a kind of parabolic sort of trajectory. It doesn't matter if my parabola is a bit wonky or a bit lopsided or something like that. It doesn't make any difference. Okay, so we've got S, U, V, A, T, and remember, S, U, V, and A are vector quantities, and I'm going to be expressing them as column vectors. We're not going to need all of these quantities. In fact, we're not going to need V. Okay. The other quantities we're going to need, and the vector quantities, I have a tendency to use column vectors rather than IJ notation, but it doesn't make any difference. It's just personal preference. If you prefer IJ notation, use that, but do bear in mind that these are vector quantities. Okay, so S is, that's actually what we're looking for. We're looking for an expression for S because this is our vector, effectively OP. U is U cos alpha, U sine alpha, meters per second, acceleration. Okay, so evidently this kind of sets the theme here that I'm taking upwards as positive. I don't have to, but this, I didn't actually necessarily realize this as I was writing it. It was just subconscious. I'm subconsciously here taking upwards as my positive direction. In the vertical direction, I'm also taking that direction, so from left to right, as my positive direction in the horizontal direction. Now, maybe be aware of this on some level, even if it's not a conscious awareness. Just be aware that you do need to have kind of selected positive directions in the vertical and horizontal direction. Okay, so the acceleration here is going to be 0 minus g meters per second squared. Okay, so sometimes people who haven't necessarily fully grasped the idea of vectors and choosing positive directions might just write 0g here, which kind of contradicts what you've got here. Now, if you'd written here, or if I'd written here, minus u cos alpha and minus u sine alpha, then 0g would be the correct expression to write here. Okay, or even if I'd written u cos alpha minus u sine alpha, if I'm taking downwards as positive and still taking that direction as positive. There's various combinations. There's no right combination. It's just that whatever you do has to be consistent with the choice that you make. Okay, t, that's a scalar quantity anyways, t seconds. Okay. Right, so the Suvat equation that I'm going to use is obviously going to be S equals ut plus half at squared, which is u cos alpha, u sine alpha times t plus a half 0 minus g t squared, which I can group all together into ut cos alpha and ut sine alpha minus a half g t squared. Okay. I emphasize again, this is the displacement. It is a vector. This is not the distance. Okay, but I do want the distance. So if this is OP, the vector OP, then what I really want is OP in magnitude, the magnitude of OP. Because that's going to give me an expression for the distance from O to P. Actually, it's not going to be this that I'm going to use. I'm going to explain why in a second. Because this turns out to be a little bit cumbersome. I'm going to just make a slight modification to it. But let's just stick with this. So what I get is ut cos alpha squared plus ut sine alpha minus a half gt squared squared. Now, the magnitude of OP is going to be the square root of all of this. I don't want that, okay? I don't want the square root over all of this. The reason for that is something which I anticipated when I went through this problem was I'm going to be differentiating this function. Okay, I'm going to be differentiating it. If I've got a big square root symbol over it, it's just going to make it more complicated. So what I'm going to do instead is I'm going to deal not with the distance OP, I'm going to deal with the square of the distance OP. So the rationale here is that I'm going to be looking effectively at the turning points, the gradient of this, the maximum points, minimum point, whatever is going to be applicable. So let's say I've got two numbers, x and y, that are both positive. Okay, we're not dealing with negative numbers here, they're both positive. And I know that x is greater than y. Then I know that x squared must be greater than y squared also. Now this wouldn't work if x could have positive and negative numbers. So for example, 3 is greater than minus 4, but 3 squared is not greater than minus 4 squared. But if I'm restricting x and y to just positive values, then I can deduce this. This is an if and only if, okay? Imply if and only if. Implies and is implied by. This is the kind of idea that I'm going to be using. So if I want to maximize the value of the distance function, OP, let's say, then I can get the same result by maximizing the square of the of the distance function. If I want to minimize the distance function, because remember, the distance is always positive, right? Distance is always positive. So if I want to minimize the value of the distance function, then I could minimize its square and still get the same results, so to speak. Okay, where OP, the magnitude of OP, the values of t for which OP is going to be maximized or minimized, is going to be the same as where the magnitude of OP squared, the same values of t where OP squared is going to be maximized or minimized. Okay, so it's using this kind of idea. So I can simplify this, and what I'm going to get is u squared t squared. I'm going to get cos squared alpha from here, and I'm going to get a sine squared alpha from there. So that gives us a nice simplification. Minus, and it's going to be gut cubed sine alpha plus a quarter g squared t to the fourth. Okay, so I mean there's various ways that I can write this. I can write it as OP squared, I could write it as modulus of s squared, whatever. Okay, in fact, let's go for that. Let's go for the modulus of s squared. Okay, so that's, oh, which simplifies even further. Almost forgot. That's just 1 minus g/ut cubed sine alpha plus a quarter g squared t to the fourth. Okay, right. So what I'm interested in doing now is, because I'm interested in when this distance function is always increasing. When it's increasing, then the gradient function must be positive. Okay, so I'm interested in when the gradient function of this is going to be positive, because that implies whenever the gradient function is positive, the distance is going to be increasing. Okay, so you've got to make sure that you're able to relate this sort of these kinds of information, bits of information, with each other. Okay, so it's make sure that you understand how to interpret differentiation, how to apply differentiation, and things like this. It's one thing being able to do differentiation, but it's a very different thing understanding when and how it can be applied and how to interpret it and things like that. If you're doing a step paper, I'm presuming that you don't really have too much difficulty understanding how differentiation can be interpreted, but just make sure that you are, you are familiar with those ideas. So just to reiterate, what I'm looking for then is, in order to guarantee that this is always going to be increasing, I want the derivative or the gradient function of this to always be positive, or at least for the duration of the journey, the flight of this particle. Okay, so I'm going to make a note of this expression because we are going to need this later. So s is equal to ut cos alpha and ut sine alpha minus half gt squared. So just in case I lose that, because I don't have a tendency to just rub things off the board. So what I'm interested in then is differentiating this thing. So we get d by dt of the modulus of s squared, and that's going to be equal to 2u squared t minus 3 gut squared sine alpha plus g squared t to the third. Okay. Right, so this factorizes. I can take t out as a common factor. T 2u squared minus 3gu sine alpha. And I'm going to write it in this way because I want to emphasize here that I'm looking at this here. I'm going to need to view this as a quadratic expression in t. It's not a quadratic in u. U is a constant. T is my variable. So I am going to be viewing this bit as a quadratic in t. That's going to be important for the calculations that I'm going to be doing in a second. Okay. So what we're looking for where the derivative is going to be greater than 0. Okay, positive. Okay, so I mean, I can see that when t is equal to 0 here, t is either 0 or positive. When t is equal to 0, the derivative is going to be equal to 0. Okay, but we're not really interested in t. We can see from what we've got here that when the particle is projected, initially the distance from the origin is going to increase. It has to, okay? If it was 0, then the particle wouldn't actually, unless u was equal to 0, and the particle doesn't actually move away from the origin, then this is kind of irrelevant, okay? t equals 0 is going to be irrelevant. So for all intents and purposes, t is going to be positive. So that leaves us with this then. So what I'm interested in is, under what conditions is this always going to be positive? There's a couple of ways that I can go about doing this. There's the first way, which I'm going to show you. And then there's the second way, which I'm going to show you when it comes on to the next part of this problem. Okay? Because when I initially went through this problem, what I looked at was the discriminant of this quadratic expression. But when I went on to the next part of the problem, there was something that came up that made me choose, that made me do something to solve the next part of the problem, which upon further reflection, I realized that thing that I do to solve the next part of the problem, I could actually have used to solve this part of the problem as well, and potentially faster. Now, this is not something to be concerned about. If you solve a problem in a particular way and then you happen to find a better solution to your problem further down the line, that's how it should be. Okay, your first attempt at solving a problem is usually going to be less than ideal. I'm not going to say bad, but often it's not going to be the best way. As a mathematician, though, what you're going to be interested in is, once you've got your solution to a problem, actually reviewing it and seeing, is there anything that you could do better? And sometimes the things that you can do better will become apparent as you work into the problem. Okay, it can be a little bit frustrating sometimes because you've done something, you get a bit further into the problem, you've got a better understanding of the problem, and you think, oh, I could have done that better. I should have seen that. Oh, but you didn't. Okay, your understanding of the problem deepens as you get further into the problem, and it's natural for you to start seeing things that you could have done better earlier on. And it's tempting at that stage to actually go back and kind of start all over again with this better solution. My advice is to make a note of it, make a note of what your idea is, so that you can go back later, but actually carry on with your, just carry on with the rest of the solution. Okay. It can be very tempting to just cut off and go back and with your better idea or something, but this is part of the fun of problem solving. This is what makes problem solving interesting to mathematicians, is this, you're making these new connections all the time. So, okay, let's have a look at the discriminant of this. So if this is a quadratic in t, so I want to guarantee that this is always going to be positive. Now, I know that it's going to be positive because the distance is increasing initially. But not only that, it's a positive quadratic in t. Okay, so if it's a positive quadratic in t, it's going to have this sort of shape. So it cannot remain entirely below the horizontal axis. It can't. Okay, it has to be at some points above the horizontal axis. So if I can show then that this doesn't have any real roots, or find suitable values of alpha, or even suitable values of sine alpha, for which this doesn't have real roots, then I can guarantee that this curve will always be above the horizontal axis. Okay? How can I do that? Discriminant less than 0. Okay? Identifying those values of sine alpha for which the discriminant is going to be less than 0. So let's have a look at that then. What's the discriminant of this? It's going to be minus 3gu sine alpha squared minus 4 times 2, for a is g squared times 2u squared, which is 9g squared u squared sine squared alpha minus 8u squared g squared. And we need this to be what? Less than 0. Why less than 0? Because that's the condition that guarantees no real roots. Okay, less than 0. So if that's the case, g squared, u squared cancels, and what do I get? 9 sine squared alpha is less than 8. So sine squared alpha is less than 8/9. Now remember, alpha is between 0 and pi by 2. So sine alpha is going to be positive. So there's no danger of me here, when I square root here, getting negative values or anything. It's the positive square root that I'm going to be looking at. There's also no danger that the inequality symbol is going to switch around or anything like that. So I get sine alpha is less than 2 root 2 over 3. Okay. So that's what I needed to show. So just to check against the problem, show that if sine alpha is less than 2 root 2 over 3, then the distance OP is increasing throughout the flight. So what we've shown here is that sine alpha is less than 2 root 2 over 3. The gradient function is always going to be greater than 0, is always going to be positive, and therefore the distance is always distance of P from the origin is always going to be increasing. Now, what I would highly recommend that you do in your exams is that you put some kind of explanation to what you're doing in your calculations. Do not just present a bunch of calculations, okay? You won't see this in textbooks. Your teacher shouldn't do this. I'm not doing it here, okay? Even though I'm just writing these on the board, I am explaining to you what they mean, what my calculations mean. Now, it's easier for me to do that in words here because I can do it through the video for you. In your exam, your medium of communication is your exam script, okay? Writing. So you need to show your examiner that you know why you're doing these calculations, why you're looking at the discriminant of this, and why you're setting it equal less than 0, and what the interpretation is. Don't balk at having to do this, because this is part of your solution to the problem. Okay. Yes, your examiner will know, even if you don't put these comments there, will kind of know what you're doing. They will know how to interpret these calculations, but you need to show your examiner that you know how to interpret these calculations and that you're not just fluking it. Okay. This is an essential part of your solution, to actually explain yourself. Okay. Why you're doing the things that you're doing. Notice that I'm not just standing here writing things on the board and expecting you to know what I'm talking about or what I'm doing, why I'm doing the calculation. I'm explaining to you. You have to explain to your examiner. Very important in STEP for you to do that, and very important if you are going on to higher level mathematics that you continue to do this. Okay, so that's the first part. So that's the way that I did this originally. There is, in my opinion, potentially a better way of going about this. So let's have a look at the next part of the problem, okay, which will kind of tie into the other way that we can go about solving this. So what's the next part of the problem? Show also that if sine alpha is greater than 2 root 2 over 3, then OP will be decreasing at some time before the particle lands. Right. This, to me, is a part of this problem where a lot of people, I think, would go wrong. Okay, and it's just speculation, but I think there's a very easy trap for people to fall into here if you're not careful. Because I think there's potential for misunderstanding, and it's nothing to do with the question being poorly worded. The wording of the problem is fine. It's what people might be, because the results, because based on what we've done here, it would seem very clear that if we just change these inequality symbols around, we get the solution to the second part, right? Because if I just set this greater than 0, that means that if this is a positive quadratic, then it will have real roots. It'll have two real roots. So therefore, it must become negative at some point. So that means that the gradient function will be negative, and therefore the distance OP will be decreasing for some values of t. So all I've got to do, right, is just change these inequality symbols around. Well, that's wrong, unfortunately. Or not necessarily wrong, it's only part of the job. Okay, you've only done part of the job, because what have you shown here? And again, you have to show that you know what you're doing. Okay, very important. So what have we done here? We've shown that for some values of t, this is going to be negative, and therefore this is going to be decreasing for some values of t. But wait a minute, what does the question, what we asked to show? Show also that if sine alpha is greater than 2 root 2 over 3, then OP will be decreasing at some time before the particle lands. Okay, so what if the values of t for which this is negative are effectively after the particle has landed? In other words, when the model is not actually valid anymore. This model is only valid for the duration of the flight of the particle. So what if the turning point, not the turning point, where this becomes negative, sorry, what if that occurs after this point here, at a value of t over here somewhere? We've got to figure that out, okay? And this is why it's really important for you to first and foremost, you yourself understand what you're doing, but also then demonstrate that you're understanding to other people through explanation and things like that. Okay, so this is perfectly useful information. This tells us that we do have roots and that this will sometimes be negative. But unfortunately, it's not sufficient for what we need. What do we need to know? Well, we're going to need to know when the particle actually lands. Let's have a look. So when does the particle land? Well, it's going to be whenever this second component of this vector is equal to 0. So let me do it up here. So I can take t out as a common factor. So t times u sine alpha minus a half gt is going to be equal to 0. So that means that t equals 0, or t equals 2u sine alpha over g. Okay, so in other words, this time here is 2u sine alpha over g. So what I need to show is that this function is going to be negative for some values of t less than this. Okay, so how might I do that? Well, the first thing that I tried to do, which was in retrospect quite naive, but I gave it a go anyway, was to actually try to find expressions for the roots of this quadratic. Okay, remember this is a quadratic in t. So what you get is something like t equals 3g u sine alpha plus minus the square root of 9g squared u squared sine squared alpha minus 4 times g squared times 2u squared over 2g squared, I guess. So you get this, and you can fiddle around with this, but I probably spent 5 or 10 minutes trying to mess around with this, trying to get something out of it, simplified expressions, and it just wasn't working. Okay, I'm not saying that it can't work. Maybe it needs somebody that's got a bit more adept with algebra than I am, maybe. I don't know, but I just couldn't get anything out of it that was going to be useful to me. Okay, so I thought, right, okay, so there was something that I mentioned earlier that might be quite useful here. That this is a positive quadratic. Right? So it's positive quadratic and it's got real roots. We know we're interested in when it's got real roots, so that it drops below the horizontal. Aha, okay, so maybe this could work. Maybe I could find the location or the coordinates, maybe, if necessary, of the vertex of this quadratic. Right? This is because it's a positive quadratic. It's going to have a minimum point. The minimum point, if the function is negative, the vertex must be below the horizontal axis. And if I can show that this occurs at a value of t that is less than this value of t, then I've cracked it. okay? I don't even need to worry where the roots are. I know that at least one of the roots then is definitely going to be less than this. So how can I find that? Completing the square, of course, right? Completing the square on what? On this thing here, right? So we've got g squared t squared minus 3gu sine alpha plus 2u squared. This is going to be equal to gt minus 3u sine 3 halves u sine alpha squared minus 9/4 u squared sine squared alpha plus 2u squared. Okay, couldn't even write identically equal to. So the minimum occurs at t equals 3 halves u sine alpha. Don't forget about the g here. 3 halves u sine alpha over g. The reason I'm pointing that out is because at some point when I first went through this, I did make an arithmetical error somewhere, or an algebraic error, should I say. I messed up with the g's somewhere, which made things really, really difficult, unsurprisingly. So just be careful with your algebra. Easier said than done. Even after all these years, I still make mistakes with algebra. It happens. Just be on your guard. That's all I can say. Okay. So why is this useful to us? Because I can see that this is less than 2 u sine alpha over g. 3 halves, obviously less than 2. U sine alpha, g, they're all positive. Therefore, I get that. So the minimum occurs at a value of t which is less than the value of t when the particle actually lands. Okay, so what that tells me is that this will be negative for some values of t before the particle lands. Now, I still need to show. I'm going to kind of discount this. I'm not going to use this. I still want to show that this will happen for values of sine alpha greater than 2 root 2 over 3. Okay, so I've kind of already done it here using the discriminant, but I'm going to use the completed square form to show you how that's going to work, how you can derive the same result from this. So we've shown where the minimum occurs. Now we need to look for the conditions on sine alpha to guarantee that it's going to be negative. The value of the function at that time is definitely going to be negative. So what does that mean? I need 2u squared. The value of this at this value of t is this here. Okay, just remember how to interpret completed square form. 9/4 u squared sine squared alpha. And I need this to be less than 0. So I can cancel through by u squared, and I get 2 minus 9/4 sine squared alpha is less than 0. Sine squared alpha, therefore, is going to be greater than 8/9, and therefore I get sine alpha is greater than 2 root 2 over 3. Bingo. Okay, that's exactly what I needed to show. So for values of sine alpha greater than 2 root 2 over 3, the minimum value of the function is going to be less than 0. I know that the minimum occurs at this time, which is less than the time, the value of t from when the particle lands. Therefore, I've shown what I needed to show. Okay, so again, make sure you clearly write your interpretation of these things in your exam scripts. Don't leave it to your examiner to guess what you mean, or to fill in any gaps. Your examiner's not there to fill in the gaps in your solution. Okay, try to the best of your ability to explain what you're doing. Okay, so this could also be used. This idea of completing the square could also be used for the previous part when we wanted to show that for values of sine alpha less than 2 root 2 over 3, the distance OP is increasing throughout, because we could again complete the square, and we could solve rather than solving 2u squared minus 9/4 u squared sine squared alpha is less than 0, we could just flip the inequality symbol around. We wouldn't even need to know where the vertex occurs in that particular case, because what we get is that the function is always above the horizontal axis. Okay, when I'm talking about the curve, I'm talking about the curve that represents the gradient function. It's always above, so it's not at certain values of t and things like that. It's always above. So that would be a much slicker way, potentially, of dealing with the first part of the problem as well. But it's entirely up to you which you go for. Just accept that sometimes there might be different ways of going about things, and really, you know, if as you progress into a problem you see something that you could have done better, okay, it's no big deal. Right, so then on to, I've got my notes here just to quickly refer to. So the next part of this is not too difficult, it's just a little bit messy algebraically. So what we've got is, at the same time as P is projected, a particle Q is projected horizontally from O with speed v along the ground in the opposite direction from the trajectory of P. The ground is smooth, and show that if 2 root 2 v is greater than sine alpha minus 2 root 2 cos alpha times u, then QP, the distance QP, is increasing throughout the flight of P. Okay, so there's a lot of information there. Let's see where we get to with this one. So here we've got Q, which has been projected in this direction with speed v meters per second. Okay, so that's Q. So now I need to find an expression for the distance QP rather than the distance OP. So obviously this is going to be varying now. So it's going to be varying as P and Q move along their respective trajectories. So we've got, rather than having a fixed point with respect to, you know, which we're measuring the distance P, we've actually got a variable point now. Okay, so how are we going to do this? We need to find the position vector of Q at time t, which is fairly straightforward. Again, it's suvat. So S is equal to, that's what we're interested in, U is equal to minus V0 meters per second. And again, I'm taking that direction as positive, so because Q is going in that direction, it's going to be minus V. V we're not interested in. A is equal to 0 meters per second squared. Actually, this, I'm making more work here than I really need to, aren't I? It's just going to be S equals V times T, basically. U times T, sorry. U times T, which is minus VT0. To cut a long story short. Kind of unnecessary, but we got there in the end, right? Okay, so in this case, we've got QP, which is going to be equal to so I'm talking about the vector here, maybe QP, the vector from Q to P or from P to Q, whichever, it really doesn't make any difference. So from Q to P, so I'm going to go, it's going to be VT 0, and then from O to P plus, so this is the negative of this vector because I've gone kind of that way, plus ut cos alpha, ut sine alpha minus half gt squared, which is equal to ut cos alpha plus vt and then ut sine alpha minus half gt squared meters or whatever. Okay, and it's going to be a similar thing here. So we're looking at the distance QP squared, which is going to be the square of that cos alpha plus VT squared plus UT sine alpha minus a half GT squared. Again, I'm using the little trick of squaring the distance function to avoid any unnecessary square root signs. This can be expanded and simplified, so I'm going to get u squared t squared. So I will get u squared t squared cos squared alpha from here and sine squared alpha from there, which is, when I group them together, just save a bit of time, I'm going to get u squared t squared plus 2u v t squared cos alpha plus v squared t squared plus, I've already dealt with the u squared t squared sine squared alpha, minus ut cubed times g sine alpha plus a quarter g squared t to the fourth. Okay, time for a little break. Okay, so I can take t squared out as a common factor there. So let's, rather than rewrite it all out, let me just erase that. T squared. Okay, so what I'm interested in now is the derivative of this with respect to t. So that's going to be twice u squared plus 2uv cos alpha plus v squared t minus 3 UGT squared sine alpha plus g squared t cubed. Okay, I'm going to have to refer to my notes here because it's a little bit fiddly, the calculation for this. So, again, we're interested in when this gradient function here does not have real, because we're interested in when the distance QP is increasing. Okay, so again, we're looking for where can we guarantee that this is always going to be positive? How can we guarantee that this is always going to be positive? So I can take t out as a common factor from here. So I get t times 2u squared plus 2uv cos alpha plus v squared minus 3ugt sine alpha plus g squared t squared. Again, I'm going to view this as a quadratic in t. U and v are fixed quantities, bear this in mind. So the quadratic, it is a quadratic in t. Yes, t could be equal to 0 or positive. We're not interested again in when t is going to be equal to 0. Okay, so how can we do this? Well, I think that there is the possibility of going again for maybe completing the square, but that's not the way that I'm going to go this time. I am going to look at the discriminant of this on this particular occasion, just because that's what I did. Okay, it might be possible to complete the square and use that technique, but I'm actually going to use the discriminant on because that's just what I did. Okay, so there's no suggestion with this that this is a model solution or anything like that. If you want a model solution to this, check out the mark scheme and you'll find a model solution. What I'm trying to do here is to kind of emphasize the difficulties and the messiness of the problem solving process. Okay, I've kind of highlighted a few of these throughout this video. That's the whole point really of these videos. It's not to present model solutions. And I'm also not suggesting that my solution is necessarily the best solution. It's just my solution. And that's why I'm going to stick with what I did rather than trying to change it at this point. I'm going to stick with what I did. And that was checking the discriminant of this thing. So this expression here is going to have no real roots when 3ugt sine alpha, or technically minus 3, squared minus 4 times g squared times 2u squared plus 2uv cos alpha plus v squared is, so what we're looking for, no real roots, so it's going to be less than 0. So this is the discriminant of this quadratic expression here. To guarantee that there's no real roots, set it less than 0. Okay, I'm going to have to clear a bit of space now because I'm going to need some. Okay. Right, so I'm going to have to keep referring to my notes for this one. So, okay, so it's 9u squared g squared sine squared alpha times t squared minus so 8u squared g squared plus, so it's going to be minus, don't forget about the minus sign here, minus 8g squared 16 g squared uv cos alpha minus, again, don't forget about the minus sign, minus 8 v squared g squared. And this needs to be less than 0. Okay, so have I missed anything out? I don't think so. I hope not. So what I did was then I kind of took this to one side. So the 16 g squared uv cos alpha minus 8v squared g squared, and it looks like, so I did this a few days ago, it looks like I actually no, there was something that I did before that. I cancelled the g squared. Okay, so I don't need the g squared in here, which is good. And okay, I completed the square on this, treating it as a quadratic expression in v. Okay, so I got 8v squared plus 2uv cos alpha, so that gives me 8v plus u cos alpha squared minus, okay, I want to get this right, u squared cos squared alpha, which is 8v plus u cos alpha squared minus 8u squared cos squared alpha. So then I replace this with this expression here. So we get 9u squared sine squared alpha times t, sorry, there shouldn't be a t in there. Just realised, no, because this is the discriminant, isn't it? So there shouldn't be a t squared in there. Sorry for that. Minus 8u squared minus 8v plus u cos alpha squared plus 8u squared cos squared alpha, and that has to be less than 0. Again, I'm going to have to check my notes because I'm really losing track of where I'm going with this, to be honest with you. So, what did I do? That is less than, okay, so I brought all of that over to that side. So 9u squared sine squared alpha minus 8u squared is less than 8v plus u cos alpha squared plus 8u cos squared alpha greater than u squared. Aha, okay, right. So bring that, yeah, okay, that should be a minus. Okay, so I left a u squared sine squared alpha over here, minus 8u squared is less than 8v plus u cos alpha squared minus 8u cos squared alpha. So I've subtracted 8u squared sine squared alpha from both sides, I'm leaving 1 u squared sine squared alpha over here. So I get minus 8 u squared sine squared alpha. So what's going to happen here is I'm going to get just 8u squared. Okay, so I've got cos squared alpha plus sine squared alpha, just 1. 8v plus u cos alpha. So I've got u squared sine squared alpha minus 8u squared. Cancel, cancel. And keep missing off my squares. So then take the square root of each side. I get u sine alpha is less than 2 root 2 v plus u cos alpha. Okay, and what is it I needed to show? 2 root 2 v is greater than sine. Okay, so bring the 2 root 2 u cos alpha over here. So I get u sine alpha minus 2 root 2 u cos alpha is less than 2 root 2 v. Take u out as a common factor. Sine alpha minus 2 root 2 cos alpha times u is less than 2 root 2 times v, which is what I needed to show. Okay, so it took me a while to figure this out, by the way. So don't be put off if sometimes it does take you a while to figure out what to do. This is entirely normal with a step problem. They're designed so that you have to think very carefully. And if you do find with step problems that the solutions are just kind of flowing out of you, then either you're extremely, extremely intelligent, you've got an IQ of about 250 or something, or you're doing something wrong. You're really missing something, because there should be some hard work involved. Okay, so that was my solution to the final part of this problem. It really was just a massive algebra crunch, but there are some quite subtle things that you've got to do. So like here, for example, recognizing that you've got the 9u squared sine squared alpha here, and you can think about it as u squared sine squared alpha plus 8u squared sine squared alpha. How do you know to do stuff like that? It really just depends on the context. Okay, there's some things that I've written here that actually I could have done it a bit faster, but again, I'm not too bothered about that. Okay, once I've got my solution to the problem, then I can start looking at ways to refine it. So again, this is not supposed to be a perfect model solution, far from it. This is just me presenting my solution and the kinds of ideas that I had when I initially went through this problem. Okay, explaining the kinds of difficulties that I might have encountered and so on. So that brings us to the end of this problem. If there is anything that you're not clear about, that you want me to explain to you a little bit more clearly, please leave a comment in the comments section. I don't make any money from making these videos. I make these videos because I want to help people prepare for their A-level exams, step exams, MAT exams, and I would like to continue making these videos. Please show your support by hitting the subscribe button and hitting the like button to this video, so that I know that there are people out there that are getting some benefit from these videos, and that will encourage me to keep making them. So if also you know anybody else that might benefit from these videos that's preparing for the A-level exams, please feel free to share these videos with them. Encourage them to show their support as well. But that brings us to the end of this problem. It's been a long problem, it's been a long video, but thank you for watching, and I'll see you in the next video. Thanks a lot, guys.